Hello everyone and welcome back to my Continuum mechanics lectures. We will start with some preliminaries which are required for our study of continuum mechanics. So we'll start with vector and tensor algebra. Start with vector algebra. The first thing we want to look at are vector spaces. So a vector space or a linear space V, capital V, is a set of vectors, say A, B, C, and so on, plus two operations which are addition and scalar multiplication, such that the following properties hold. So this can be, we'll take some vectors and some scalars. So vectors are defined as A, B, C belonging to V, and scalars are defined as alpha, beta, gamma belonging to the set of real numbers R. So the first property is that of closure, which is defined as alpha of A plus beta of V also belongs to V for some alpha beta. So for some AB belonging to V and alpha beta belonging to R, that the scalar multiplication of some vector and addition to some other scalar multiplication to another vector also belongs to the same vector space, should also belong to the same vector space. The second property is that of associativity, that is A plus B plus C is equal to A plus B plus C. So what this means is that, say for example, A plus B is uh, some vector, say D, which by the first property of closure should also belong to V. So what it says is that D plus C is equal to A plus, say, B plus C is equal to M. So M also belongs to V. So these two vectors are equal. The third property is commutativity with respect to the vector addition. That is, A plus B should be equal to B plus A. The fourth property is that of an existence of a null element. That is, there exists a vector which belongs to vector 0 which belongs to V, such that a plus 0 gives us the same vector. The next property is the existence of an additive inverse. So for each vector A belongs to B, there exists B belongs to B such that A plus B is equal to the null element 0 vector. So we say that B is equal to minus of A. The next properties are related to the scalar multiplication aspect. So so uh, again coming back to associativity. So alpha beta of A is equal to alpha of beta of A. The next property is distributivity. There are two types of distributions possible. There's alpha plus beta of A is equal to alpha of A plus beta into A. And the second one is alpha into A plus B should be equal to alpha of A plus alpha of B. The last property is that of the existence of unity of identity. That is, a scalar exists which when multiplied with a vector gives us the same vector. Now we'll look at the linear dependence and independence of vectors. So what does a set of vectors being linearly independent or dependent mean? So first we will look at linear independence. So let v1, v2 to vp, a set of p vectors, be a set of elements belonging to V. This set is linearly independent if alpha 1 v1 plus alpha 2 v2 and so on until alpha p vp is 0. This implies that alpha 1 is equal to alpha 2 and so on equal to alpha p is equal to 0. This means that for the first statement to be true, if v1 v2 until vp are linearly independent, that should mean the corresponding coefficients, scalar multipliers, should also be 0. So what then becomes linearly dependent vectors? So if this equality, if alpha 1 v1 plus alpha 2 v2 until alpha p vp is equal to 0 with at least one of alpha 1 to alpha p non-zero, that is, this condition is not satisfied. Basically, this statement does not imply this condition, alpha 1, alpha 2, alpha until alpha p, all the alphas be 0. Then we say that the vectors, these vectors v1 to vp, are linearly dependent. So it's important to note that, just put in here, that the 0 vector is linearly dependent. That if you take any vector a and you multiply 0 to it, it gives us the 0 vector. So and this violates the condition of linear independence, that none of the scalar, none of the alphas can can be non-zero, should be non-zero for linear independence. Now, using the concept of linear independence, we classify the dimension of the vector space V. So V is finite dimensional if there is an integer n such that any linearly independent set of vectors in V has at most n elements. In shorthand, a linear finite dimensional, say n dimensional vector space can be written as Vn. For our interest, n is always less than equal to 3 because we want to eventually work in three-dimensional space. So we'll now come to what is known as a basis. So how is a basis? How is a basis defined? Any set of n linearly independent vectors in Vn. It should be an n-dimensional vector space. Forms a basis for Vn. So let's say we have a basis for Vn defined in terms of the vectors u1 to un. So the set of vectors u1 to un form a basis of Vn. Then any vector v belonging to Vn can be written in terms of these written in terms of these vectors u1 to un as a linear combination of them. So can be written as a linear combination of ui. I I is from 1 to n. So what how we write it is like this: alpha 1 u1 plus alpha 2 u2 till alpha n un. So this can be proved. So we'll look at the proof of this. So since Vn is n dimensional, we saw previously that V is finite dimensional if there is an integer n such that any linearly independent set of vectors in V has at most n elements. So, so the highest number of linearly independent vectors in V, if V is n dimensional, is n. So that means that the set of vectors, the set of vectors V along with the n vectors u1 to un has to be linearly dependent. Which can be written as lambda v plus lambda I ui, I goes from 1 to n, is 0 with at least one of lambda and lambda i's non-zero. Now lambda cannot be 0 because that would mean I mean if lambda is 0, if lambda is 0, then that would imply sigma lambda I ui equal to 0, is equal to 1 to n. As ui's are a set of linearly independent vectors, that would mean all lambda i's are 0. But that violates our claim that the set of vectors v u1 u2 until un has to be linearly independent, which means that one of the uh, one of the scalar multiplication multipliers has to be non-zero. So that means lambda is not 0. Then Let us say that then let alpha I is equal to minus lambda I by lambda, which implies that v is equal to alpha I ui, which proves our initial statement that any vector v belonging to Vn, it can be written as a linear combination of the basis vectors ui. And it can be shown that I'll leave it for you to prove that the coefficients are unique for every vector v. Next, we will talk about what we'll be regularly require in our discussion of continuum mechanics and Euclidean vector spaces. So how are they defined? These are n-dimensional vector spaces endowed with a dot product that is u dot v. The product belongs to the set of real numbers such that the following properties are followed. That is, u dot v is equal to v dot u, which is commutativity with respect to the dot product. U dot v plus w is u dot v plus u dot w. The third is alpha u dot v is equal to u dot alpha of alpha into v is equal to alpha u dot v. And the last is an important property, is that the dot product of a vector with itself is always greater than equal to 0. And if the dot product is 0, that implies that the vector itself is 0. The non-zero vector cannot have a dot product with itself to be 0. We'll define a few important quantities associated with the dot product. First is the norm of a vector. It's associated with the, so in 3D space we know that u dot u, the norm of u. So let's first define what's the norm of u. Is the dot product of the vector with respect with itself. So it's the notion of length of a vector, the magnitude of a vector. So we say that a given vector u is a unit vector if its norm is 1. Put out the Cauchy-Schwarz inequality, which states that u dot v is always less than or equal to the product of the norms of the two vectors. There is also the triangle inequality, related to the norm of a vector, that u plus v is always less than or equal to u plus norm of u plus norm of v. That is, say for example, we have a vector u and a vector v, and the triangle u plus v forms with the two vectors. So the length of any side of a triangle is always lesser than the sum of lengths of the other two sides. So this is what this triangle inequality mentions. We'll come to orthogonality now. Say suppose we have two vectors u and v belonging to the Euclidean n-dimensional Euclidean space. They are orthogonal if u dot v is 0. Using this property of orthogonality, we can define a set of vectors to be orthonormal as well. Orthonormal would mean that a set of vectors u1 to un is orthonormal if any two vectors ui uj, the dot product of any two vectors of that set is 0 if I is not equal to j and 1 if I is equal to j. That is, say for example, u1 dot u1 is equal to norm of u1 should be 1, but u1 dot u2 is 0. These two vectors are orthonormal or orthogonal. And the property of orthogonality plus all the vectors being unit vectors, these two combine to give us a set of orthonormal vectors. So they are mutually perpendicular, mutually orthogonal unit vectors. Here we will introduce the notion of the concept of the Kronecker delta. We'll talk more about it later when we talk about Einstein summation convention. Which is defined as delta ij is 1 if I is equal to j and 0 if I not equal to j. So therefore, so given our set of orthonormal vectors, we can write this definition ui dot uj as delta ij. So ui dot uj is equal to delta ij if u12 un is a set of orthonormal vectors. So for an n-dimensional Euclidean space, an orthonormal basis can always be constructed. Say those basis vectors are termed as E1 to En. It may always be constructed. So for example, the Gram-Schmidt procedure is one of the processes to construct orthonormal basis from a set of n linearly independent vectors. They are not necessarily unit vectors. They can be any vectors, but they are linearly independent and they belong to the n-dimensional Euclidean space. So an orthonormal basis can be constructed from those set of vectors. So as we had seen earlier, that for an n-dimensional vector space, any vector v, uh, any vector v can be written as a linear combination of n uh, linearly independent basis vectors. So similar can be done with our orthonormal basis vectors. That is, for any vector v belonging to the Euclidean n-dimensional Euclidean space, v can be written as a linear combination of the orthonormal basis vectors E1 to En. Is written as a sum. This can be written as a sum. This is a scalar vi. So these vi's are components of v with respect to the basis vectors ei. So for example, we can have another orthonormal basis. Let's say f1 to fn furnishes another orthonormal basis of En. So we can be written in those in terms of those basis vectors also, but the components uh, will be different. So these are components. I don't want to say different, but they will not necessarily be the same. Let's put it that way. There can be two basis vectors according to which we can have the same. Actually, not, because as you had seen that in the note we put out here the coefficients of alpha i's are unique for each v. So by that proposition, the components with respect to different bases and different orthonormal bases will be different. Components of v with respect to fi, they are different from these vi's, which are components of v with respect to ei. And let's look at let's look at the summation convention, the Einstein's summation convention. So this is a technique used to ease a just write it, which actually makes the use of vectors, makes the use of components very easy for easy to be written and easy to write basically. So when we write, we say suppose a vector is written in terms of the basis vectors vi ei in terms of components with respect to the basis vectors. This is written in shorthand as v is equal to vi ei. This summation symbol is omitted. So when we write v as v, when we write this statement, we mean that v is v is written as I is equal to I goes from 1 to n vi ei. That is, without writing the summation symbol, we assume that I goes from 1 to n. That is, we agree to sum over the range of index which is prescribed. So here this is I. So here we can see that the index I is repeated twice. One of the rules of the summation convention is that an index I is a repeated index or a dummy index if it's used on one side of the equation more than once. If an index is not repeated, then it's if an index is not repeated, then it's called a free index, and it should exist on both sides of the equation. So for example, say vi is a function of some is written in terms of other quantities such as t ij xj. So here j is a repeated index and I is a free index. So that means that say I and j go from 1 to 3. So v1 is t11 x1 plus t12 x2 and t13 x3, and so on with v2 and v3. So here j is a repeated index and I is a free index. That is 1, when I is equal to 1, then this is our expression. Same for 2 and 3. So we'll look at a few examples which will ingrain into us this idea of summation convention. We'll see how easy it makes it for us to write these vectors, and further we will look at tensors also represented in the same form. So, so the first example we will look at is that a dot product of V with EJ. And EJ is one of the orthonormal basis vectors. So this, when we write V as VI EI using the summation convention EJ, uh, this can be written as VI EI dot EJ using the property of dot product. Let's see where it was. Using this property of the dot product. And as we had defined earlier, using the Kronecker delta, EI dot EJ can be written as delta EJ. What does this mean? So now here we see that J is a free index as it exists on both sides of the equation, and I is the repeated dummy index. So what does this mean? That this can be written as V1 delta 1J plus V2 delta 2J plus V3 delta 3J. And as J also goes from 1 to 3, so we are restricting ourselves to three-dimensional, n is equal to 3, three-dimensional Euclidean space. So we know that only one of the, depending upon J, only one of these Kronecker delta values will be 1, other if and the rest two will be 0. So it will only be 1 when, so say if J is 1, then this one will be true, then this will be, so let's write it like this. So this is V dot EJ is V1 if J is equal to 1, V2 if J is equal to 2, and V3 if J is equal to 3. That means that V dot EJ is VJ. Note that here there is no sum. It's just one quantity because it exists as a free index on the right hand side. If there had been some dummy index, then we assume that it is a sum. That is an important distinction to make using the summation convention. So for an orthonormal basis EI, any vector can be written as, in terms of the dot product, V dot EI. The components Vi are written as V dot EI. Let's look at a second example. Let two vectors UV belong to the Euclidean n-dimensional Euclidean vector space, where U is written as UI EI and V is written as VJ EJ. Taking the dot product of U and V, we have UI EI dot V is equal to ui ei dot v. Now ei dot v is vi, so this is ui vi. Now as this is a repeated index, we mean that this is equal to u1 v1 plus u2 v2 until un vn. The summation is implied when we use a repeated or a dummy index. Next, we will look at a representation theorem, which is known as the finite dimensional Rees representation theorem. So what this states that let f of v be a scalar valued function of vector v. That scalar valued means that f of v is a scalar. That for a vector v belonging to the n-dimensional vector space, n-dimensional uh, vector space, Euclidean vector space, sorry, f of v gives us a scalar which belongs to the set of real numbers. If f of v is linear, that is f of alpha 1 v1 plus alpha 2 v2 is equal to alpha 1 f of v1 plus alpha 2 f of v2 for all v1 v2 belonging to the n-dimensional Euclidean space and alpha 1 alpha 2 belonging to the set of real numbers, then there exists a constant vector A belonging to the n-dimensional Euclidean space such that f of v can be written as A dot v. Let's look at the proof of this. So f of v can be written as f of viei, which can be further written as, according to the property of linearity, this one. This can be written as vi f of ei. The summation is implied, which is v1 f of e1 plus v2 f of e2 and so on until vn f of en. Now these f of e1, f of e2, f of en, these are n constants independent of v. That is independent of, why they are independent of v? Because they are independent of the components vi. They're only dependent on the orthonormal basis vectors. Vi. We call them as, they're called as AI. So f of AI, f of, sorry, f of EI is EI, AI, a scalar. As f is a scalar valued function, we can write it as AI. Therefore, f of V becomes AIVI, which is, as we have seen before, A dot V. Again, something which can be shown easily. I would like you to prove it for yourself that A is unique. That is, for a given function f of V, which is linear, scalar valued function f of V, which is linear, which can be written as A dot V. This A is unique. Next, we'll be looking at the vector product or cross product, and we'll be sticking to three-dimensional Euclidean spaces. So, if let's say we have two vectors belonging to the Euclidean three-dimensional Euclidean space, then the vector product U cross V, which also belongs to E3, U cross V is such the following properties are followed. It is U cross V is negative of V cross U when the vectors are interchanged. The second property is that U dot V cross W, where W also belongs to E3, is equal to V dot W cross U, which is equal to W dot U cross V. This can be written in this form, which is called a scalar triple product and the box product. This quantity belongs to the set of real numbers. So we can see that this is a cyclical, that this equality holds when this cycle is followed, that when u, v and w are in this order, that u dot v cross w, u dot v cross w is equal to v dot w cross u is equal to w dot u cross v. If one of them is interchanged, then this negative sign appears. The third property is that the norm of u cross v is equal to the norm of u, multiplied with the norm of v, the sine of the angle theta between the vectors u and v. The dot product is defined as norm of u into the norm of v into cos of the angle between the two vectors. The next property is that it's the cross product is distributive. That alpha u plus beta v cross with w is equal to alpha u cross w plus beta v cross w. We'll look at some interesting properties and features of the cross product. So the first one, from the rule 1, that is this one, we see that if we if we take v to be the to be the vector u, that is u cross u is equal to minus of u cross u. This implies that u cross u is 0. Similarly, in 2, we replace w with u. We get u dot v cross u is equal to v dot u cross u is equal to u dot u cross v. Now, as this is 0, u dot v cross u is equal to u dot u cross v is equal to 0. Similarly, when we replace w with v, we get that v dot u cross v is 0. What does this mean? This means that u cross v is orthogonal to both u and v. The next we see a few properties of the box product. U w, the first one. The box product is linear in each argument. That is alpha 1 u1 plus alpha 2 u2 vw is equal to alpha 1 u1 vw plus alpha 2 u2 vw. Same can be done for v and w as well. Second property is the box product changes sign if any two entries are swapped, that is UVW is minus of VUW. These properties can be easily proved with the four rules that we saw earlier. These one, two, three, four. Okay, this sheet has finished, so I'll start on a new sheet. I'll continue on a new sheet. Let's look at the third property. So let E1, E2, E3 be a right-handed orthonormal basis. We'll come to what right-handed means in a moment. First, we'll write it in terms of expressions, that E1 cross E2 is E3, E2 cross E3 is E1, and E3 cross E1 is E2. So if we take three orthonormal vectors E1, E2, so this is E2, C3. So putting our hand in the direction of E1 and curling it towards E2, the thumb should give us E3. And similarly, putting our hand towards E2, curling it towards E3 should give us E1, and putting our hand towards right hand, the hand in question is the right hand, putting our hand in direction of E3 and curling it towards E1 should give us E2. That is what right-handed orthonormal basis means. So we'll define a quantity using the box product as Eijk to be Ei, Ej, the box product of Ei, Ej, Ek. So how is this defined? From the earlier properties and the rules for the vector product, we can easily see that Eijk is 1 if Ijk is a cyclic permutation of 1, 2, and 3. That is 1, 2, 3. If this cycle is followed, then Eijk is 1. That is, for example, E1, E2, E3. This is equal to E1 dot E2 cross E3, which is from this definition E1 dot E1, which is 1. This is minus 1. Eijk is minus 1 if Ijk is 1, not a cyclic permutation of 1, 2, 3, and I, j, k are all different. So for example, if we say that if we look at the box product of E1, E3, E2, what would this be? E1 dotted with E3 cross E2. This is negative E1. That means that minus E1 dot E1 is equal to minus 1. Coming back to the completing the definition of Eijk, this is 0 if any two or all three indices are same. So our from the property we looked at when two of the vectors of the box product were same, then the box product was 0. So this 0 value comes from that property. So this definition can be used in a lot of ways. So for example, we have two vectors. We take the cross product of two orthonormal basis vectors. This can be written as from our definition of, so we had defined V as V dot EI. So this can be written as EI, or say EJ cross EK dot EI. This is same as writing EIJK EI. So any vector, so for vectors A, B and C belonging to E3, if we define C as A cross B using this definition, so let's suppose we write C as CIEI, A as AJBJ, AJEJ, and B as BKEK. So A cross B is AJ EJ cross BKEK. That means AJ BK EJ cross EK. I write it here. That means that using this definition, we can write it as EPS EIJK AJ BK EI, and this is equal to CIEI. That means CI is equal to EIJK AJBK. So the components of the vector C, if C is defined as A cross B, the components can be written easily in terms of the permutation symbol. This this is known as this EIJK is known as the permutation symbol. This EIJK has another very important application in to write the components to write the determinants of matrices in component form. So let Bij be a 3 cross 3 matrix. So it's written as B11, B12, B13, B21, B22, B23, B31, B32, B33. Let capital B be the determinant of Bij, which is written as the same. This can be written as in the in this form: Eijk, Bi1, Bj2, Bk3. This can be easily seen if you do it yourself. If you write all the components, if you write the determinant in terms of the components, you can easily see that this expression is valid. So what we'll do is that we will apply the permutation symbol on both sides of the equation. Then we get, say, EMNP B is equal to EIJK BIM BJN BKP. which is which is same as writing this form: B1M B1N B1P B2N B2N B2P B3N B3N B3P. Further, it can be shown that if we multiply again Eijk on both sides, B, then this becomes, the right hand side becomes BIN BIN BIP BJM BJN BJP BKM BKN BKP. Let Bij be our Kronecker delta delta ij. Then the determinant, that is in terms of matrix, it can be written as one, the identity matrix, which the determinant of this is, that is B is 1. The determinant of the Kronecker delta written in terms of written as a matrix is 1. So what do we so when Bij is delta ij, then what does this equation become? That is Eijk EMNP is delta IN delta IN delta IP delta jm, delta jn, delta jp, delta km, delta kn, delta kp. So now we will look at, so uh, this is one of the epsilon or E delta identities. We'll look at some more such identities. So this one is A. So let's say this is A. And B would be obtained as, let's say K is equal to P. Then this would be EIJK, EMNK. What does this mean? Delta IM, delta IN, delta JM, delta JN, delta IK, delta JK, delta KK, delta KN, delta KN. What do we get when we write it in terms of, when we expand it in terms of the expression of the determinant? So delta Km, delta In, delta Jk minus delta Jn, delta Ik minus delta Kn, delta In, delta Jk minus delta Jm, delta Ik plus delta Kk, delta In, delta Jm, sorry, Jn minus delta Jn, delta In. Now what is delta Kk? This is delta 1 1 plus delta 2 2 plus delta 3 3, which is equal to 1 plus 1 plus 1, which is 3. Therefore, evaluating the expression Eijk, Emnk further, what do we have? We'll open the brackets up. Delta Km, delta In, delta Jk, delta Km, delta I, am I right? Yeah. Delta Jk minus delta Km, delta Gm, delta Ik, delta Jm, delta Ik, sorry, yeah, minus delta Kn, delta In, delta Jk, minus delta Kn, so Kn, delta In, delta Jk, delta Jm, delta, sorry, delta In, delta Jk, Im, delta Jk plus, sorry, delta Kn first, delta Jm, delta Ik, and plus 3 times delta Im, delta Gm minus delta Gm, delta In. So we'll look at these terms. So delta Km, delta In, delta Jk. This can be written as delta Jk, delta Km, delta In. This term can be written as, so this is a repeated, the K is a repeated index here. So what does this mean? Delta J1, delta 1m plus delta J2, delta 2m plus delta J3, delta 3n times delta In. So these terms, delta J1 is only 1 if J is equal to 1, and similarly delta 1m is only 1 when m is equal to 1. Similarly for the other two terms as well. So when is this whole quantity equal to 1? When J is equal to m. When is this quantity equal to 1? When J is equal to m. Similarly for this quantity as well. So this can be written as, the K can be omitted, and this can be written as delta Gm, delta n. All the terms, wherever there are repeated index in terms of K, they can be merged. Therefore our expression Eijk Emnk becomes delta In, delta Jm minus delta Jm. I've written something wrong. What is the second term? This should be Jn. My mistake. Sorry. This is Jn. Again, delta Jn, delta In minus delta Im, delta Jn plus delta Jn, delta In plus 3 times delta In, delta Jn minus delta Jm, delta In. So we can see that this term occurs twice, and this cancels out 2 out of 3 times this one. So this is cancelled. Similarly with this term, this cancels the 3 times of this term. So what we are left with is so this is our second E delta identity. The third is when J is also equal to E, that is Eijk The final thing for today's lecture, we'll see how the components of a vector change with the change of basis, and we'll get a relation between them. So say we have two orthonormal bases, sorry, EI and EI prime. These are two orthonormal bases in En. So a vector V, the vector V doesn't change. A vector V is a vector V, right? In a vector space, in the Euclidean n-dimensional Euclidean space, a vector V is a vector V. It doesn't change with respect to the two bases. Its components may change, but the vector itself doesn't change. So the vector V written in terms of the components with respect to the EI basis should be equal to the components and the basis vectors written in terms of the basis vectors EI prime. Now Vi is written as V dot EI and Vi prime is written as V dot EI prime. Now, EIs can also be written as in terms of the EI prime basis in the following form. It's simple. It's replacing VI with EI, EJ. This is written as AIJ, which is the matrix of direction cosines. Why there are direction cosines? Because we had seen earlier that u dot v, there's no need to put the mod here. U dot v is u, or a norm of u, norm of v cos theta, where theta is the angle between u and v. So ei dot ej prime would be norm of ei, norm of ej prime cos theta. Ei and norm of ei is 1 and norm of eij prime is 1 because they are unit vectors, because they form an orthonormal basis. So this is equal to cosine of the theta, cosine of the angle theta between them. So that's why they are known as the matrix of direction cosines. Therefore, ei is equal to aij ej prime. So going back to our expression of vector in terms of the components, v is equal to vj prime vj prime and is equal to vi ei. Ei can be written as aij ej prime. Therefore, vj prime vj prime is equal to vi aij ej prime. Taking it on the left hand side, we have vj prime minus aij vi aij prime is equal to 0, which means that so this here we invoke our definition of linearly independent vectors again. So the ej primes are all linearly independent vectors, and this is a scalar. These are scalars. So this is equivalent to writing alpha I ej prime is equal to 0 for linearly independent vectors ej prime. So which implies that all the alpha i's are 0. That means vj prime minus ai jvi is 0. Hence vj prime is equal to aij vi. So the components of a vector in one orthonormal basis of En can be written in terms of components of the same vector in another orthonormal basis of En if the direction cosines, the matrix of direction cosines between the two orthonormal bases unknown. So that brings us to the end of the discussion vector algebra. In the next lecture, we will look at tensors, and that's it for today. Thank you.